Alrighty. I realized I have not done a single check your understanding video yet for this unit on inference procedures with means, and so it's time to change that. Unfortunately, it's going to take a hot minute, and I got stuff to do. So I suggest you strap in and get ready to pause things if you need me to slow down. Let's see where I am starting. All right, starting with that 10.1 constructing confidence intervals for means. And I'm going to try to get all the way through 11.2. Let me share my screen. And let's see here. Yep, this is where I want to be. All right, I was trying to make sure that my stuff in Google Chrome was set up right, so we're ready to go. And just ignore how much stuff I have open. All right, first set of questions. Yeah, I'm going to turn my audio or video off because I don't like looking at myself. Thanks. Here we go. Use table B to find the critical value T star that you would use for a confidence interval for a population mean in the following settings. If possible, check your answer with technology. So a 98% confidence interval with a sample size of 26. Don't forget, that means my degrees of freedom is quite simply 25 and minus 1. And, oh, it's going to be easier if I leave it here. And so then I go to the formula sheet, scroll down to my T distribution, 98% confidence interval with degrees of freedom of 25. My T value is 2.485. And I want to confirm that using technology. So remember, the idea is that 98% is of, or 0.98 is the area in between. I'm going to use this critical value. So I'm going to do an inverse T with an area of 0.99. Remember, there's 2% in the tails, and I'm now including one of those tails because it's everything less, and degrees of freedom of 25 again. So using technology, because I love living in the 21st century. Statistics, yeah, I could go to distributions and probability or statistics, but inverse T, 0.99, degrees of freedom, 25, and 2.485 it is. Sweet. So technology is telling the same story. So now 99% confidence interval for a simple random sample of 85 observations. So what's the confidence level? 99%, 85. So here's the issue with using a formula or the table here is one, it's hard, it's easy to get lost, but two, they don't have exactly 85. So you have to go round down to make sure you have enough area in that critical value, or yeah, and widen that interval out enough to have the right capture rate. So T equals 2 point, I think it was 2639. The beautiful thing is I can do technology to get a more precise T value. And so this time 0.99 is in the middle. And so the area I'm going to use is 0.995, right? There's 1% in the two tails, split it in half to get everything below. Inverse T with that area and a degrees of freedom of 84. And so for the savvy person, you can just hit enter with this, modify these numbers correctly, and 2.636, that's pretty close to what we got. Notice that's a little bit narrow or smaller, again, because we were able to use a higher degrees of freedom. So you can do the whole thing again, though, inverse T, if you're not comfortable with how I got there. Same exact answer. All right, moving on. National poll of a random sample of 1,640 adults was carried out by morning consult. Each morning, or each person reported how much they or their significant other spent on an engagement ring. The histogram displays the results. Determine if the conditions for constructing a confidence interval have been met in this context. I gotta say, that is gross that there's that many people spending 15,000 plus. Just my own personal wisdom on this or thoughts on this. My wife knew I loved her without me spending $15,000 on a ring. It is better to set yourself up for success and than to burn out all the money you have on a ring like that. All right. So, conditions. Do I have random sampling? And random sampling is stated, so I'm good to go on that one, right? It is safe to say 1,640 is less than 10% of all engaged slash married people. I say that because it's not just the people that are engaged, but engaged or married. And that was actually a fun fact. I'd have to go back and find the data, but there's actually a pretty decent correlation between a more expensive engagement ring and a higher divorce rate. I'd have to go and find that data, and I don't remember why, like what the explanation of that correlation is, but I do remember that correlation. We might look at that when we see bivariate data later in a week or so. Sorry for that aside. Now, that's a heavily skewed sample or distribution for a sample, but the sample size is 1,640, which that is um, definitely sufficiently large. Large to satisfy the central limit theorem. All right, there's the end of that. Hopefully that makes sense. Again, checking conditions, random 10% if sampling without replacement. And we need a sampling distribution that is approximately normal. We now have that with the central limit theorem. All right, 10.2. This one, not sure why I have anything written here, but let's look at it. Construct and interpret a 99% confidence interval for the mean weight of garbage for all households in this community. So we have a random sample of 15 households. All right, so here we go. Choose. When we choose, we got to choose that procedure. So we are doing a one sample, because it's only one sample. We got to do a T interval for a population mean. We are trying to estimate some population mean where mu is the true mean weight of garbage for all households in this community. My guess is this is a weekly mean weight, but who knows? Um, I still need a confidence level, 99% confidence level. Check. I got to check some conditions. We have a random sample is stated. You could do something simple if you're like, how do I show that random sampling is there? You could draw an arrow to it. You can just say random sample is stated. Just please do more than random and check mark. Random sample is stated. We have, I would say it's safe to assume, so I would say it that way. Safe to assume that sample size of 15 is less than 10% of all households. It'll be more clear on an AP exam if it's satisfying the 10% condition. And then we don't know the shape of the population distribution. So I don't know if the sampling distribution is approximately normal. 15 is not large enough to satisfy the central limit theorem. But looking at that graph of the sample, that sample shows no heavy skewness or obvious outliers. So it is believable. Man, I'm struggling on spelling today. The sampling distribution is approximately normal. So there's my check. Now I've got to calculate. Remember, when we calculate, we always want to start with our general formula. So what we have is statistic plus or minus a critical value times my standard error. And so this is where choosing a procedure at the beginning can be very helpful. So we're doing a population mean. So I know my statistic is X bar. I'm dealing with means and I don't have population standard deviation. So I'm using a T critical value. And then if you're not 100% on the um, formula for standard error, come on up. I've got one population. Notice I got my statistic X bar right here. I've got parameter, which we don't have. Now we don't have population standard deviation, so I can't use that. But the standard error of the sample statistic is right here, S divided by the square root of N. So S divided by the square root of N, and that gets me to a mean of 59.5 plus or minus. Now I got to go find that critical value. I've got a degrees of freedom equal to 14, right? N minus 1. And a 99% confidence interval. Yep. Okay, so formula sheet. 99% and 14 is right here. Let me check, make sure it's right. 14, so 2.977 times my standard deviation, 27.2 divided by the square root of N. And so that gives us the interval. And yeah, you could do that by hand. But I also have a calculator. Statistics, confidence intervals, t-interval, right? I've identified all these things by naming the procedure from the beginning. X bar, oh yeah, what was that sample mean? 59.5. My standard deviation was 27.2. Sample size was 15. Confidence level is 99. And so there she blows. All right, so my confidence interval 38.6 to 80.4. And so again, you can check that 59.5 plus, what was it, 2.977 times 27.2 divided by the square root of 15. 80.4 is just slightly off, more likely some rounding in the later parts of that 2.977 and 38.59, so 38.6, right? So don't have to do a whole lot more work than that. Calculate, conclude. In conclusion, with 99% confidence, the interval 38.6 pounds to 80.4 pounds captures the true mean weight of garbage for all households in the community. All right, there's 10.3. So check our understanding with 10.4. Again, confidence intervals, but now we're dealing with two means. So a large publishing company conducts an experiment with the hopes of finding ways to increase the amount of time that people spend reading. 2,025 volunteers were randomly assigned into two treatment groups. One group of 975 was not given any reading materials, while the other group of 1,050 people were mailed books that matched their interest. Here are the summary statistics. I feel like we went over this in class. Maybe not, but just to be safe, choose. Got two samples, so it's going to be a two sample. It's means, so T interval for a difference in means. Do note and remember that we are now looking at the difference between a difference in means and a mean difference. Difference of means is literally what's written right here, a difference between two means. A mean difference is where you have two samples, but you'd find the difference first and then find the mean of everything. And so be careful. We'll get to that in the next one. And so I will remind you when it's a two sample thing, I like just doing mu1 minus mu2, where mu1 is equal to the true mean time people not given reading materials will or would spend reading, while mu2 I don't like using equal sign because it's not a statement of equality. It is defining. Mu2 is the true mean time people mailed books that match interest would spend reading. So as long as I define mu1 and mu2 and I have shown mu1 minus mu2, I'm good to go there. Confidence level, 95%. Confidence level. Choose, check. If it was two samples or collecting two samples, I would have to check independence and random, but I don't because they were assigned, right? So random assignment is stated. Make sure you scour the problem and figure out if it's random sample or random assignment. This is actually an experiment with that random assignment in there, right? That is also why I don't have to check 10% condition. You only check 10% when you're sampling without replacement. So I'm randomly assigning, don't need 10%. From there, I do need to check approximate normality in the sampling distributions, but both samples are sufficiently large, N1 equals 975, N2 is equal to 1050, are sufficiently large to assume the sampling distributions are approximately normal. So choose, check, calculate. Remember, statistic my plus or minus critical value times my standard error. And so X bar 1 minus X bar 2 plus or minus a t-score times my standard error, which is going from that formula sheet. So remember, you can always go back and look at it. So S1 squared, so the variance of sample 1 divided by N1 plus the variance of sample 2 divided by N2. So remember, it really is that standard deviation divided by the square root of N, but I can't add standard deviations. I've got to add their variances. And so if I take S divided by root N and square it, that's how I'm getting S1 squared divided by N1, etc. All right. I could go ahead and plug some things in, but this is where I'm often going to jump to the calculator because I live in the 21st century. I'm going to run my confidence interval. I've got a 2-sample t interval, and I've got some statistics to throw in there. X bar 1, 7.8, 5.4, I think it was 950. Let me go check. 975. X bar 2 is 43.8. 35.5, 1050. So remember, we do not pool our data. Confidence level was 95%. So there is, well, almost my interval. There it is. And so that is the interval that we have calculated. Notice it went ahead and spit out a degrees of freedom. That's a large enough degrees of freedom. We might as well just use the Z instead of a T distribution. Yeah, so I'm going to talk about two things with the T in a second, but right now I want to just write down my confidence interval of negative 38.2 to negative 33.8. There's my interval. All right, so X bar 1 minus X bar 2, so 7.8 minus 43.8 plus or minus, I'm going to come back to that critical value, 5.4 squared divided by N1, 975 plus 35.5 squared divided by 1050. And so if I want that T, remember this is 95%, well, two things. One, I've got 1000 and something spat out from the calculator for the degrees of freedom, 1101. So if I want 95% confidence level, I don't have that specific degrees of freedom, so I just go to 1000. Simple enough, right? So that's one option. So I'm going to make a note down here. So T from table with degrees of freedom equal to 1000, right? 1101 rounded down. Because if it's not on the table, you round down to make sure it's wide enough. That T is equal to 1.9, what was it, 62? The conservative way, which sometimes they do a conservative way, the conservative method to always work is you take your smaller sample size, so 975 in this case, subtract 1 from it. So conservative gives you a degrees of freedom equal to 974. Rounded down is only 100, right? So then that T comes out to be 1.984. But you need to be aware if you're using the Inspire that it's going to give you a T based on the calculator. And so off of the calculator, we would go menu, probability, distributions. Actually, let me write that number down. 1101.19. Menu, probability, distributions, inverse T. So 0.975. Remember, it's 95% confidence interval, 5% in the two tails. Half of that's 2.5, so 97.5 comes out to be that area. Degrees of freedom, 1,101.19, 1.962. Notice this is pretty darn close to what the table gave us. And so you need to make sure that you're pretty accurate with this formula. Um, if you're just going to plug things into the calculator. All right, there's my calculations. Now my conclusion with 95% confidence, the true difference in mean time a person would, again, we got to make sure that we say would here, not in this sample, but for everybody. So a true person would spend reading if not given materials versus given materials of interest is captured by the interval negative 38.2 minutes to negative 33.8 minutes. And there we go, 10.4. All right. I'm not going to go through this procedure. The big thing that I need you to understand on this one is it is a paired test. When you do a paired test, you run it exactly the same as a, what is it called? One sample test. Goodness gracious. So, do parents realize how many hours their children are spending online? Family psychologists conducted a study to find out. Random sample of 10 teenagers was selected. Each teenager was given a Chromebook and free internet for 6 months. During this time, their internet usage was measured. At the end of the 6 months, the parents of each teen were asked how many hours per day they think their child spent online during this time frame. The dot plot and summary statistics are for the differences, actual time minus parent perception, right? So the data is paired on the individual student. So the actual time that the person spent online minus how much the parent thought, it's all centered and paired on that one student. They could very easily run this test just all of the actual times average minus all the parent time average, but that doesn't give us as clear of a picture. Construct and interpret. So it's a one sample t interval for a mean difference, and it define your parameter, right? It's the where mu sub d. Sorry, I was trying to figure out why this is different, what I need to remember. So where mu sub d is the true mean difference in the actual time a teenager spent online minus the amount of time the parent perceived they were online. But notice it's mu sub d, so it's a mean difference. A difference first, then means. And then 90% confidence, check your random. And notice the big thing here is they're not independent random samples. We have the two different pieces of data because they're coming from the same sample, right? So it's just parent versus teenager, but it's blocked almost on that one student or one person. And then it is random though. We don't have a large enough sample size for central limit theorem, but that dot plot doesn't show heavy skewness or outliers. And then you run your test. And again, when you run your test, it's just going to be X bar D plus or minus your critical value times your standard error. And the big thing I want to point out with this is when you do your T critical value, your degrees of freedom here would just be 9 because it's essentially come down to a one sample T interval. And that's how you would run the test. All right. Told you, we moving today. The AP stats teacher from East Kentwood wondered if her students' AP exam scores from the previous year were better than the scores from Rival High School to the north. She took a random sample of 10 of her students from last year and found a mean AP score of 3.8 with a standard deviation of 0.84. State appropriate hypotheses for performing a significance test. So my null hypothesis is that East Kentwood has a mean score of 3.11, but we want to know if it's better, or if they did better. So mean is greater than 3.8, where mu is the true mean score, AP stat score for East Kentwood. Do the results provide some evidence for the alternative? Heck yeah, they do, right? X bar is equal to 3. Oh my gosh. How am I letting myself do that? Sorry. If you are screaming in your seat right now, like, Mr. Kinney, that alternative is wrong, you are correct. The alternative is that the mean is greater than 3.11. So, do the results provide some evidence for the alternative? Yes, the sample mean is 3.8, which is greater than 3.11. That's evidence. That is literally in the direction of the alternative. The teacher performed the significance test and obtained a p-value of 0.014. So remember, the whole idea of a p-value is assuming, I'm going to draw a little normal distribution to help illustrate this idea. If the true mean was 3.11, the probability of getting 3.8 or more extreme by chance alone, right? Because all that stuff inside the normal distribution, that's what's expected within this many standard deviations, etc. So assuming that the mu was actually equal to 3.11, or we really should have more context in there. So assuming the true mean AP score for East Kentwood was 3.11, the probability of getting a score of 3.8 or better by chance alone is 0.010, nope, 0.014. At the alpha equals 0.05 level, do the results provide convincing evidence that the mean AP score for East Kentwood is greater than 3.11? Heck yeah, don't write that on your AP exam, but yes. Since the p-value of 0.014 is less than alpha of 0.05, there is convincing evidence mu is greater than 3.11. Notice that doesn't mean mu is 3.8. It's just like that's so unlikely to get that statistic or more extreme by chance alone that we at least think mu is greater than 3.11. So there's convincing evidence mu is greater than 3.11. Make sure if that's the first time you're talking about it, you include context there. I would make a note here. The idea again is that it is so unlikely by chance alone. We don't think we don't think there is a shot the assumed null hypothesis is right. That's why we reject it. So I know a lot of times I've had students in the past like, oh, so we want a high p-value to reject our null. And the answer is no. The p-value is how unlikely is it to happen by chance alone. If it's super unlikely to happen by chance alone, we reject our null and we have conclusive evidence for the alternative. All right, last thing we got to today because we did not finish the previous one, but another class did the same body temperature activity with these results. Use t-test on the calculator to find the p-value. So my p-value, menu, statistics, stat test, t-test, statistics, 97.9. Oh yeah, null is 98.6, 97.9. 1.6 for standard deviation, sample size of 30. Let's see, I think this is different from, so whoops, so it not equal to, right? And so we get a p-value of 0.023. 0.023. Do we reject at an alpha of 0.1? Yes. And yes. And no. So use t-interval in the calculator to find these following intervals. And so 97.4 to 98.4. 97.3 to 98.5. 97.1 to 98.7. All right. So do we reject the null hypothesis? Yes. Not an interval. Yes. Ditto. No. Is captured by interval. All right. So remember the whole idea was that mu was 98.6. So what connection do you notice between the answers to numbers 1 and number 2? If we reject the null hypothesis, then that value is not captured by the interval. And also a 90, I should say this, 90% confidence level is connected to an alpha of 0.1 with two-tailed test. 95% confidence level, that is connected to an alpha of 0.05 with two-tailed test. And 99% confidence level is associated with an alpha of 0.01 with two-tailed test. But again, the idea is that I want to emphasize is if we're capturing that value or not. If that value is not captured by the interval, we reject the null hypothesis. And so you can use confidence intervals and hypothesis test. You can use confidence intervals to check for evidence of a convincing evidence of an alternative value, but that is based on a two-tailed test and not equal to. Doesn't work as well. With one-tailed, I don't know this stuff with one-tailed as well as I should. Wish I'd give you more information, but I gotta go. So that was a quick one. but a lot of information. Hope it was helpful for you. And see y'all in class tomorrow. Or if you're not in my class and just using this, that's wild. But hope you got something out of it.